My name is Chris Morisette. I am the Novice Chair for the Houston Astronomical Society. And we're going to try something new here tonight, or at least something new for me, and that is hosting the Zoom while giving the presentation. I've gotten some offline direction from Joe Califf, and so far so good. But if I get in here into a situation with a gate crasher or any other kind of technical difficulty, forgive me if I have to pull back from the presentation and take care of that. Okay, so with that said, you there. All right, there we go. Okay, so welcome to the July Novice meeting for HAS. Tonight's topic will be twofold. We're going to be primarily going over gems of the summer sky, and then I put in a small but hopefully informative introduction on artificial intelligence and its connection, its application in astronomy research. Yep. So that is coming at the end. Before I get into the deep dive into the presentation, if you could put your microphone on mute, I would appreciate that. And then also, if you have any questions, please put them in the chat box. And then when I get done with the presentation, I'll circle back and go through the questions, and we'll deal with them like that, like we typically do. Okay, so and if at any time I'm not coming through or the screen's not showing up, feel free to come off mute and get my attention, and we'll go ahead and get it fixed. All right. So tonight we're going to be talking about a few things. First, I'm going to do a quick refresher on navigating the sky. We'll talk about summer signposts, and then we'll go through our summer sky tour. And here we'll look at various objects of interest that are great to go out and look at during the summertime months. And then again, I'll wrap up with a short presentation on astronomy and artificial intelligence. So navigating the sky. You've seen these slides before, but I think they're nice, real good refresher for going out and finding your way around the night sky. So if you haven't already, go to skymaps.com and download your copy of the July 2023 map. Again, if you're going to use this map out in the field, what you'll want to do is place the map in the upright position where the text is all legible and south is down at the bottom of the screen. While you're facing south, that will give you a picture of what the night sky should look like. And then if you are going to turn around and face north, you want to turn that map upside down so that north is on the bottom of the page. And here again, the depiction that you see on the map will be of the night sky in that particular direction. I think these maps are geared for 10 o'clock at night during the course of July. So again, that's an easy way, inexpensive way to get a nice guide for the month of July, or really any month that you're after. Again, going back to some basics here, the celestial coordinates are pretty important if you're using, especially if you're using big references like turn left at Orion or any other kind of celestial maps. Like we have on our terrestrial maps with longitude and latitude, we also have right ascension and declination. Right ascension being analogous to longitude and declination being analogous to latitude. And with those two coordinates, you can find any star, any nebula, any galaxy, any other object. You can find that on a celestial map. Remember that the celestial equator is the same as our own equator, and the celestial North Pole is the same as Earth's North Pole. The ecliptic is the plane in which the sun and the planets rotate. Well, that is where we see the sun and where the Earth and the planets orbit the sun. And for people that are familiar with the zodiac signs, the constellations that are in the zodiac, such as Leo, Cancer, Libra, Aquarius, those particular constellations lie around the ecliptic, and that's why they're referred to as the zodiac signs. I got this image, this and the next one, I thought was pretty good. It kind of shows all three of the celestial planes, if you will, in relation to Earth. So you'll see here the celestial equator, which is our is the same as our own equator. You'll see the ecliptic, and you can kind of get an idea of at what angle the ecliptic plane is to the celestial equator. And then also in here is the galactic equator, which is basically the Milky Way disk. And since we're entering summer, and we're going to be pointing back towards the center of the galaxy, and the Milky Way is going to be probably at its brightest and prettiest for us to go out and observe. I thought it would be a good idea to put this in so you could see approximately where the galactic disk would be in relation to the celestial equator. This next image is from the same source, but it shows, I like this one. It actually shows our solar system and Earth as it's traveling and in relation to the Milky Way galactic plane. So you can see very clearly here where Earth is at, say, this point up here where we were in the spring equinox. You can kind of see get an idea of why they refer to spring as galaxy season, because while this diagram is not to scale, it does show, relatively speaking, our position looking out away from the galactic disk. So in that particular time of year, we're looking out into deep space and we can see all kinds of galaxies. Whereas as we just passed through the summer solstice, back in the latter part of June, you can see that Earth's position now is pointing back towards the center of the Milky Way. So this is kind of a neat diagram, kind of helps you get your bearings, if you will, on where Earth is in relation to everything else. And it also depicts the path of the sun around the Milky Way, which is actually kind of like a merry-go-round, so to speak. So pretty cool stuff. You'll remember also that depending on the latitude at which you're observing, that will that'll have a bearing on what kind of stars you'll see and whether or not they rise and set in the night sky. So, for example, if you're at the North Pole and you're looking, doing a night of stargazing, the stars that you see will never rise and set. They'll be the same set of stars, just rotating around your head. Whereas as you move farther south, that's going to change. You'll begin to see stars rise above the horizon and set below the horizon. For Houston, Polaris is going to be at 30 degrees. So the angle at which Polaris is off of the horizon is the same as the latitude of the position that you're at on Earth. And so just remember that our view is going to be different depending on the latitude. We're able to, and since we're kind of in a southern latitude, we're able to see a lot more interesting things, I think, than our friends in the northern latitudes, say in the Dakotas or even in southern Canada. And then this is always a good one. Excuse me just a second. Grab a. Thank you. This is a good picture in that it gives you a handy way, pardon the pun, for you to use your hands and your fingers in order to tell distances out in space. So if you remember, pinky is 1 degree, 3 fingers is 5 degrees, fist is 10 degrees, hook'em horns is 15 degrees, and then the pinky and the thumb out, extended is 25 degrees. So if you're out there, you don't have a cell phone app, or you're just out there trying to challenge yourself and do kind of a unassisted navigation of the night sky, remembering this is very handy. Okay, so that's just a quick brief reminder on some navigation fundamentals. Let's get into the signposts. So I put together this map to kind of show all of the signposts that we've looked at so far to date. If you remember back in the winter, we looked at Orion. That was a very significant signpost, got us to a lot of different spots in the winter sky. In April, when we talked about the spring sky, we focused a lot on the Big Dipper and Arcturus and Spica. So that these Big Dipper plus Arcturus and Spica are kind of our second major signpost. And then tonight, we'll be introducing a couple of more signposts that'll help us in our navigation through the summer sky. The summer triangle being the first one, and then the Teapot being the second one. So the summer triangle is made up of 3 bright stars, Vega, Deneb, and Altair. And these 3 stars are very easy to find in the night sky. Currently, they are rising in the east around 10 o'clock at night. And as the summer goes on, it'll appear higher and higher at 10 o'clock at night. But you can easily spot Vega, and then Deneb is very apparent as well as our Altair. So that's a easy signpost to find in the night sky. And then the Teapot, which is lower on the horizon down in Sagittarius, that's another one that'll get us to some really cool objects. And for the Teapot, at least in my own neighborhood, I've got a lot of trees up here in Kingwood, so I'm not able to see this very well. So I've got to get out to like the dark site, something that has a lower tree line on the horizon in order to see this. And at the dark site, this is very visible. So if you're planning on doing some observing and you've got the same issues that I have, the dark site would be a good place for you to go out and do the observing. You'll also notice this green box on the map. This is kind of the area of interest for our summer viewing. What I plan on doing is taking this map and updating it for the autumn. And once I do that, I'll have a set of signposts and areas of interest for really all 4 seasons. So I just thought this would be a helpful way to train your focus on where we're going to be looking here in the summertime. The Big Dipper, remember in the spring, the Big Dipper was high in the sky, and due to the fact that it was high in the sky during viewing prime time, the 10 to midnight time frame, we were able to get to many different spots throughout the night sky. We can still take advantage of the Big Dipper in the summertime. It is lower in the night sky, but we'll be using the handle of the Big Dipper to get over to Arcturus. And if you remember the old arc to Arcturus, spike to Spica, if we can get to Arcturus, then we have a fighting chance of seeing some cool things between Arcturus and the summer triangle. And if you can't readily spot the summer triangle, you'll have an ability to navigate from Arcturus over to Vega. And once you get to Vega, you're at the summer triangle. So this is still a very useful signpost for us. We won't be taking advantage of the Big Dipper in all its glory, but we'll be able to use Arcturus. Okay, so with that introduction on summer signposts, let's get into our objects for tonight. And the first one we're going to focus on is M13, the Hercules globular cluster, and it's located in the constellation of Hercules, and it's in an area called the Keystone. And so here, remember, we'll use our signpost, we'll arc to Arcturus, and then once we get to Arcturus, if we can spot Vega, then we can get over to M13. Excuse me, I've got to, let me put that on mute. Thank you. Here's a bit more of a close-up here. So here's Arcturus. And then from Arcturus, if we draw a line over to Vega, we can get to M13. So let's go back up and just kind of walk you through that. So it's not exactly on a straight line from Arcturus to Vega, but it's pretty darn close. All right. So let's go back down here and then let's look at M13. So M13 is a globular cluster. Like I said, it is located between Arcturus and Vega. And this, so if you're looking at Arcturus and Vega, it's about 2/3 of the way from Arcturus to Vega. If you wanted to put that in terms of degrees, it's about 20 degrees from Vega. So if you're looking at Vega, remember 3 fingers is 15 degrees. Pinky is 1 degree or 5 degrees, excuse me. Then you can, I think, did I get that right? Hang on just a minute. Okay, so yeah, 3 degrees or 5 degrees, really 10 degrees is here, 15 degrees is here. So if you go 15 and 5, that's 20. And then that gets you from Vega over to the M13 cluster. So excuse me for that quick diversion. This cluster is about 23,000 light years away from Earth. It's weird. Globular clusters are kind of oddballs in that they're very old. This one is practically the same age as our own Milky Way. And they reside up in the halo of the Milky Way. So they are gravitationally bound to the Milky Way, but they don't live down in the the disk of the Milky Way like everything else. There's probably about 500,000 to 1 million stars in this cluster, and this one is. I know from light polluted skies in the suburbs, you can barely make it out with a pair of binoculars. I think if you wanted to go see this naked eye, you'd have to get to a very dark site, a place like HAS, like the HAS dark site, but probably could be done. Binoculars or a small telescope will guarantee that you'll be able to see it, though. So that's M13, a very beautiful object and a very good target to put on your list for this summer. Okay, so now we're going to get into the thick of things over here in the summer triangle. And again, the summer triangle is these 3 lines that go from Vega to Deneb to Altair. And we're going to talk about a double star here first called Alberio. And Alberio is at the head of Cygnus the Swan. It appears to the naked eye to be a single star, but if you look closely, you'll notice that they are double stars, and you'll know you're on Alberio because you'll be able to see one star is an indigo color and the other is a bluish color. I was out on the driveway Monday night, Sunday night with binoculars, and I had a street lamp pointing in my face, but I was still able to resolve the 2 stars, and I was able to definitely make out the indigo color and off and on get the blue color as well from a companion star. So very colorful pair to go view, very easy to go spot in the sky. And if you're in an area that is a little bit shaded from the street lights, that'll definitely help you out. So that's Alberio. The next object that I highly recommend putting on your list is the Ring Nebula. This is about 7 degrees below Vega. So let's see, we'll go back to 3 fingers being 5 degrees. So you had a handful, you had a pinky in there and maybe a thumb. That'll get you kind of in the ballpark of where the Ring Nebula is below Vega. And this is referred to as a planetary nebula. And planetary nebulas are really the remnants of a star that would be roughly the size of our own sun. When it's come to the end of life, it'll shed off the outer layers of gas. And then once the fuel completely runs out, the core of the star collapses into a white dwarf. This white dwarf is still hot and still giving off a lot of radiation. And that heat and that radiation is ionizing this gas and giving us this beautiful colors and detail here, beautiful shapes inside the Ring Nebula. So this is a tough one to see. You can see, I have seen the Ring Nebula through a larger telescope using an eyepiece, but what you begin to see there is really kind of a grayish haze, almost like a smoke ring. So it's not as spectacular as what you'd see in a picture like this, but nonetheless, you can still make it out and it's still distinct. And again, planetary nebulas are really cool. And this is a classic example, one of my favorite planetary nebulas out there. Okay, there's another cool planetary nebula called the Dumbbell Nebula. This one's a little bit larger in size, so a little bit easier to spot. This nebula lies about 3/4 of the way from Deneb down to Altair. So if you draw a line between those two stars, you go down about 3/4 of the way. That'll get you in the neighborhood of the Dumbbell Nebula. From a degrees standpoint, it's about 15 degrees above. Now, hook 'em horns, 15 degrees above Altair. That will get you in the ballpark as well. So again, this is another example of a planetary nebula. I think the nice thing about doing the ring and then the dumbbell is that these two nebula, planetary nebulas, they come in all shapes, all sizes, and all colors. And that's the beauty of these, depending on the circumstances when the star died, what gravitational influences were around that star, how the shedding of the gas and the collapsing of the star into a white dwarf occurs will have an influence and dictate what kind of shape you get. And you get all different kinds of shapes and colors. And again, this is a good comparison to the Ring Nebula. And that's what makes planetary nebulas so neat, because no two are alike. All right, so that's the Dumbbell Nebula. And these objects are in our galactic neighborhood, right? So these are all in the neighborhood of 1,000 to maybe 2,000 light years away. So they're all within our galaxy, and they're all, again, within that galactic neighborhood that I referred to back in the February talk, if you remember that. Okay, so those are two really cool objects. Now, the summer triangle has a lot of different objects in it. I've only covered a couple tonight. There are several more, though, that we'll be hitting on in the autumn sky tour. So if you didn't hear about something that you were interested in the summer triangle, wait till October and we'll hit that as well. I needed some material for the October meeting. So that's more to come on the summer triangle. Okay, so now what we're going to do is we're going to go down to a really cool area of the sky called the Teapot. So again, the Teapot lies along the galactic plane, and you can get there, roughly speaking, by following a line from Deneb to Altair down towards the horizon, and eventually you'll run into this asterism that looks like a teapot. And here's a closer up view of what that looks like. Um, it, the So that's one way to find it. To be honest with you, and again, this is something that you would need to be out at a dark site in order to experience. But I know out at the dark site you can make out the Milky Way disk fairly easily, and then just by following that up from the horizon, you can find the Teapot that way. So either coming down off the summer triangle or coming up from the horizon, you'll be able to find this asterism. And again, the Teapot here resides in Sagittarius. It's a part of this constellation of Sagittarius, and you'll see here that you've got this nice spout that has steam coming up, which is actually the galactic disk. It's got a lid and it's got a handle. Okay, so using those facets, we'll be able to again use this asterism to navigate up to some really marvelous objects. In particular, we'll start out here with the Lagoon Nebula and its neighbor, the Trifid Nebula. M20 is the Trifid Nebula, which you see over here to the left. And then M8 is the Lagoon Nebula that you see over here to the right. These are really cool objects, very fascinating objects. Let me just say a few things about it. In order to find these both reside about 8 degrees above the spout. So you come back up here, they're about 8 degrees from the spout, and that'll get you up to the Lagoon Nebula. Now, the cool thing about these two objects is that, at least in the case of the Trifid Nebula over here, you have several different features that you can observe. So you'll see this bluish color over here. That's indicative of a reflection nebula. So you're seeing a reflection nebula as part of the Trifid Nebula. You're seeing emissions over here in the red as part of the Trifid Nebula. It's an emission nebula. See, these dark creases are actually a dark nebula, and then there's a star cluster here in the center. So, by just viewing one object, you're getting to see 4 different types of objects. So that's really cool. The Lagoon Nebula is very cool as well. It's one of probably 2 nebulas that you can see naked eye. So, in the winter sky, M42, the Orion Nebula, is one that you can easily see with the naked eye. And M8 is also one that you can see naked eye. Now, I'll be honest with you, I have never seen this naked eye, but I am going out to Fort Davis in a week for a weekend of astronomy, and I've got on my to-do list to go out and see if I can spot M8 naked eye. So pretty excited about that. These 2 objects, again, are in our galactic neighborhood. They're roughly 4,000 to 5,000 light years away. So again, these are on the Milky Way disk. That's where a lot of nebulosity is. So it's not surprising to see a lot of nebulas on the list. Okay, so that's M20 and M8. The next one is the Swan Nebula, and again, it's not very far away. So to find the Swan Nebula, what you want to do is go 10 degrees up from the handle of the Teapot, and that'll get you up to the Swan Nebula. This is an emission nebula located in Sagittarius, about 4,200 light years away. And this one has an extremely bright region here in the center. And what that actually is a combination of emission, gas ionization, and reflection from some really bright stars reflecting off of dust and other material that's in that part of the nebula. So again, a very bright, distinct nebula. You don't have to go very far from M20 and M8 to get there. So again, really cool one to put on the observation list. Moving along, we'll go up to the Eagle Nebula. The Eagle Nebula is about 12 degrees above, and I don't know if I'm sorry if I didn't mention this. Yeah, I probably did, but the Swan Nebula is 10 degrees above the Teapot lid. The Eagle Nebula is about 12 degrees above the Teapot lid. And again, here's another emission nebula. Now, the Eagle Nebula is really cool because if you remember back when Hubble first sent out its pictures of the cosmos, the pillars of creation really caused a sensation. The public adored it. It was really an awesome feature, and one that has been studied a lot for its star creation abilities. So, the pillars were really beautiful and colorful in those Hubble pictures, but you can still see those even in an amateur photo here on the screen, and that's what we're looking at here are the three pillars of creation that you see that show up in that Hubble picture so much. And again, the Eagle Nebula is just a real crowd pleaser. I know at the observatory coming up this summer, we'll be showing this a lot. And again, showing people the pillars of creation, talking about it as a star forming region is really cool. All right, so that's the Eagle Nebula. And now what we're going to do is we're going to move down a little bit back towards the horizon, towards Scorpius, which is another constellation right next door to Sagittarius. By the way, these two are both zodiac constellations, so they fall along the ecliptic. And what we're going to do here is we're going to actually wind up our discussion tonight on the objects that we were looking at by looking at a couple of open clusters, M7 and M6. And so if you can get to Scorpius, again, by kind of going down towards the horizon, following the galactic cloud towards the horizon, you'll be able to find Scorpius. It's this collection of stars here. Off the tail is where you'll find M7, and then a little bit over to the upper right is M6. These are both within about 5 degrees of the tail of Scorpius, so they're relatively easy to find. M7 is first mentioned by Ptolemy back in 130 AD as the little cloud following the stinger of Scorpius. So and this is also by, you could have guessed it, it's called the Ptolemy's cluster, and that's what you see over here. And then M6 is just its companion cluster. M6, you'll know you're on M6 because there is a very bright star, BM Scorpii. It's an orange supergiant. So if you're looking at M6 and you can spot an orange bright star, then you'll know you're in the right cluster. And then here are a couple of more directions here. And then finally, here's a picture. So here is M7 down here, and here's M6 up here, and you can see that bright orange giant here in M6. Now, I was looking at an old photo that I took from last July when I was out at Fort Davis, and I was trying to do a night photography shot of the Milky Way. And so I looked at it on my phone, and lo and behold, I had both of M7 and M6. I could barely make out the orange supergiant, but there it was. And so I actually didn't know it, but I had a picture of these two open clusters. And then really off to the edge of the top of the picture, I believe I got the Lagoon Nebula in there too. But when I go out there next weekend, I'll double check on that. So anyway, you never know what you'll find in pictures that you've taken of the stars and planets and the moon. Here is a summary of the objects that we talked about tonight. So again, here are my viewing options that I would suggest, and a lot of these are naked eye, which is really great. But at worst, you'll need maybe binoculars or a small telescope to see a lot of these. I'm going to take a pair of binoculars out with me. So with this list and my binoculars in hand, hopefully I'll be able to bag all these items when I'm out at Fort Davis. So, and then there's also some other upcoming celestial events during the course of July. So there was a couple of meteor showers. You've got the Southern Delta Aquards, last approximately mid-July to mid-August. with a maximum near the end of the month. And then the Alpha Lyrids, which happen during the middle of July and reach a maximum right at the middle of the month. Joe Califf had sent out a note here earlier, and in one of the documents that he had included, it talked about the 3 rocky planets being able to see all those at once. So definitely wanted to get that on the list. This will be occurring the 19th and the 20th. And I think on the 19th, not only will you see these 3 planets, but you'll also see the moon, crescent moon. And this will be in view about 30 minutes after sunset and kind of west near the horizon. So again, some other celestial events coming up this month that are definitely worth checking out if you've got the time and if we've got the weather. And when you go out there, be sure to take bug spray and make sure you hydrate. And I'm going to take a sip on that note. Thank you. Because it is hot. It's cooled off a little bit with the rain, but unfortunately the rain doesn't help us very much with astronomy. Okay, so bottom line, get out there and stargaze, and I'm going to certainly try and do my part next weekend, weather permitting. And with that, we'll switch gears and talk about astronomy and artificial intelligence. Okay, so why the interest? I want to talk a little bit about that. I want to talk a little bit about what artificial intelligence is and how we've encountered it in our daily lives. I then want to make a tangible link to astronomy, show you, do a little bit of a description of the Cosmos Webb research project that's going on the Webb telescope, and describe how AI is being used in that endeavor. And then also just kind of give you a summary list of where else AI is being employed in astronomy. Okay, so why the interest? I'm somewhat of a news junkie. CNBC is kind of my background noise during the course of the day. And I have been hearing about artificial intelligence, both as a productivity tool and as an investment almost daily for at least the last 2 or 3 months. So it's been out there. I've been getting bombarded with it. And I thought, well, gee, maybe there's something here that I need to dig into a little bit further. So that's kind of where, in the news is kind of where it really kind of hit me in the face. I've always been fascinated by HAL. So if you're familiar with the movie 2001: A Space Odyssey, which came out in 1968. So, and I saw a first run of it. So it kind of dates me. And I thought after I saw that movie, I thought it was one of the dumbest movies I've ever seen. But over the course of the years, I've grown to be fascinated by it and really amazed at how forward thinking this movie was. Okay. So what you see here is a picture of 2 astronauts that are on this mission to Jupiter. There's Dave Poole and Frank Borman. And in the background here is HAL. The HAL 9000 is the supercomputer that's running a lot of the mundane life support functions, but it's almost considered kind of like a third crew member. Anyway, to make a long story short, HAL had been making some mistakes, and Dave and Frank got a little bit suspicious of HAL. And so they were hatching a plot to disconnect HAL and go to manual control. Well, in order to hatch this plot, they had to get into a space that they thought was secure and turn off the sound transmission so that HAL couldn't hear them talk about how they were going to disconnect the HAL. Unbeknownst to Frank and Dave, HAL was lip reading what Frank and Dave were saying. He got wise to the plot. And, well, if you haven't seen the movie, I don't want to spoil it, but a lot of hair-raising things go on after that lip reading by HAL. So HAL is the first experience with AI that I think I can point to in my life. And that's what kind of got me interested as well. And then finally, astronomy. Modern astronomy is really becoming big data. And I went back and I put together this chart to kind of give a picture, if you will, of how much data these various research projects are dealing with during the course of their life. And so you see this, the Hubble Space Telescope down here, generating about 12 gigabytes of data per day during the course of its mission. Now, one thing I wasn't able to tell is if that was what it was at the beginning, what it was at the end, or if that was an average during the course of its life. So it's a little bit squishy there, but nonetheless, it's relatively small. And to give you an idea of how much data that would be, on a typical evening of doing astrophotography out at the dark site, look back on some of my projects, and I had been generating somewhere in the neighborhood of about 10 to 15 gigabytes of data. So roughly the same. As time has gone on, though, you can see the data generation has really climbed. So the James Webb Telescope has a 55 gigabit of data per day rate. And I got to believe that the reason that it's as low as it is because of the distance it is from Earth and the transmission windows that it has to contend with. So, and the weight and all the other things. But it's still 55 gigs of data a day. The dark energy project at the McDonald Observatory at UT is about 78 gigs a day. The transiting exoplanet survey satellite or tests had generated about 330 gigs a day, which is a lot of data. The Solar Dynamic Observatory, about 1,500 gigs of data a day, and then which is about 1.5 terabytes. And then the Vera Rubin Legacy Space Legacy Survey of Space and Time will be generating about 20 terabytes of data. So 1,000 gigabytes is 1 terabyte. And they'll essentially be performing a survey of the night sky once every 3 days. So the data that is having to be dealt with is tremendous. And the one thing that this slide really doesn't give you a feel for is the level of scrutiny and analysis that the data has to undergo. So I may generate 10 gigs in a night out at the dark site, but it's well within my capabilities because the analysis that I'm doing is nowhere near as heavy as what's happening in these research projects. Okay, so that's just kind of to give you an idea, kind of put a picture, put some numbers on big data. So let's talk a little bit about what artificial intelligence is. So you'll see this large overarching bubble called artificial intelligence. Development of smart systems and machines that can carry out tasks that typically require human intelligence. So at a high level, at a simple level, examples that you probably run into in your everyday life, real simple one is spell check on Word and the Word document. It's a very simple form of artificial intelligence. Siri or Alexa, if you use that, those tools will take create a voice file from your command. They'll send that out to a set of servers and then use some natural language processing techniques or algorithms to decode that and put it in terms the machine can understand. And then once it understands what you're asking, it'll then send back some rules-based responses to you. Very similar in nature to what a chatbot would do. So if you've ever dealt with an airline or brokerage firm or any other retail organization online, more often than not, the first step will be to type in a message to a chatbot, which is a manifestation of artificial intelligence. Some chatbots are better than others. I've kind of had a hit and miss with chatbots, especially with United Airlines and Fidelity. Sometimes they're brilliant. Sometimes it's like, just connect me to the operator, please. So anyway, a little editorial comment there. There's a more sophisticated, and so these tools that I just described are really going out and looking at the internet in general. They're going out and collecting information, processing that, and then using it to answer your question. A more refined version of this is found when you employ machine learning. So what you're doing here is you're creating algorithms that can learn from data and make decisions based on patterns. It does require some human intervention when the decision is incorrect, but it's a more refined application of machine learning. And so an everyday example that you may have run into here would be Google Maps. Google Maps used to be just a straight set of data or information that you get from a GPS satellite, but they've enhanced the functionality of Google Maps so that now you have pictures that are taken and stored in a database that Google Maps can use to better tell what address you're at, reroute you away from traffic jams and things of that nature. So by employing machine learning, they've made Google Maps more sophisticated, more functional for you. And then when I talk a bit about the example of the Cosmos Web project, hopefully you'll have a better feel for what I'm talking about. There's a third layer that you can employ called deep learning, and that's using artificial neural network to reach accurate conclusions without human intervention. I'll be honest with you, this part of AI is something that I really had a hard time wrapping my head around. I don't know how the brain works, which is where the neural network comes from. I guess the best way I can think about it is just you're building a software or hardware structure that is more closely architected like the brain, and as a result is able to make decisions and function more independently. So that's kind of my layman's neophyte description there. Okay, so let's look at the Cosmos Web project. So the objective of this project is to and again, using the Webb telescope, is to survey 500,000 galaxies using the near-infrared camera. And what they want to do is find the oldest, most fully evolved Morpheus. And what Morpheus is, it's a machine learning model that is, okay, I'm getting, are you still with me? I just got a message saying that my internet was unstable.
You went out there for a minute, but you're back.
Am I back? Okay. Was I out for a lot?
Probably about 10 seconds.
Okay. All right. Real good. Thank you. Okay. So again, the objective is to survey 500,000 galaxies, find the oldest, most fully evolved galaxies. They'll be using Morpheus, which is a machine learning model that employs a neural network. And this artificial intelligence system will be examining image files from the Webb telescope pixel by pixel to pick out blurry blob-shaped objects. And then they're going to determine, Morpheus is going to determine whether these objects are galaxies or not. Okay. Now, here's where the machine learning really comes into play. They're going to train Morpheus. And in order to train Morpheus, what researchers have done is they've collected about 76 galaxy images taken from Hubble that had been checked by human astronomers. And then they're going to use this collection to train Morpheus on a supercomputer at the University of California, Santa Cruz. So they're using this data that has been, for lack of a better term, scrubbed or had the quality of the data checked. And then they're going to train Morpheus and see how Morpheus does compared to the human astronomers. And then what they'll do is they'll retrain Morpheus as initial data is received and analyzed. So that's a real, to me, that really was kind of a good picture of how this machine learning can be employed and what it means. And so that's Morpheus in a nutshell. The cool thing about Morpheus is they're looking to reuse this on the Vera Rubin Legacy Survey of Space and Time project. So they're going to be doing a lot of similar activities on the LSST project. And hey, once you've got Morpheus trained and going, you just clone a version of Morpheus, give it to LSST, and let them employ that artificial intelligence functionality on another project. Okay, so how else is AI being employed in astronomy? So here we talked about the Webb telescope and Vera Rubin using, how it could employ Morpheus. They're also looking at using AI to find transit events such as supernovas. So one of the things that Vera Rubin's LSST project is going to do, since it's taking kind of a snapshot of the night sky every 3 days, they'll be able to use those snapshots to identify transient events, in particular supernovas. You can imagine with that much data and the pattern recognition that have to go into there and the speed at which they'd want to do this work, AI is going to play a big role. Exoplanet discovery and analysis. So we talked about how they're going to do that with TESS. I believe they're going to be doing the same thing with the Giant Magellan Telescope when it is completed near the end of this decade. They used AI on the Solar Dynamic Observatory to characterize and understand solar weather. That they're going to be employing or have employed AI to help gravitational wave detection on LIGO, and then also to detect gravitational lensing down at 3 different observatories, the Cerro Tolo, Keck, and the Very Large Telescope. So when you hear about AI in the news and you think about some of the examples you've been exposed to in your everyday life, and you want to tie it back to astronomy, here's how you could do that. Has a fairly prominent place, and I got to believe that it's only going to grow in importance. All right, so that's what I wanted to cover with AI. Before I take your questions, I just want to remind everybody about tomorrow night's general meeting. There'll be evidence for volcanism on Venus from observation to laboratory, and our speaker will be Justin Filiberto from the Astromaterials Research and Exploration Science Division at the Johnson Space Center. So be sure to tune in for that tomorrow. And let's see, let me go up here and see what we've got. Okay, you can is okay. Deborah asked, was there some talk about having a beginner's astronomy course? Has there been any progress getting that started? All right, real good question, Deborah. I know I talked to Joe Califf about that. I know he had in the back of his mind a plan to do that. What I did do is I reached out to Joe and I offered to take what outline he has for that course and develop that out further and get it deployed. I haven't heard back from Joe yet on his outline. I'll touch base with him again. And but yes, that's an important thing. I have some energy to do that. I have the added advantage that I'm retired, and I know Joe's got a day job. So with any luck, I'll get that outline from him and begin to pursue that. What I'd like to ask is if anybody has anything that they would like to see in a beginner's astronomy course, you can reach me at Chris M at astronomyhouston.org. Send that out to me. I'd love to hear from you. And again, I'll reach back out to Joe here in the next week or so. But thank you for that question, Deborah. And I think that was the end of the questions. So I'll open it up to the floor just before we stop for the evening. Does anybody else have any questions that they'd like to ask at this time? If you do, please come off mute and go ahead and ask your question.
Chris, I'll just make a comment, which I just typed, and that is that we do have a lot of kind of how-to talks on our YouTube channel until we develop a course, which are the sort of the first things you might want to learn in astronomy. One that goes into detail about telescopes. One, we have all the seasonal talks, and they cover some sky navigation. And there's one about how to set up your telescope. So you might search through the YouTube channel, Houston Astronomical Society, and see if there's something you want to learn there until a course is developed.
Excellent. Thank you, Debbie. Appreciate that. Debbie knows much more about what's available out there than I do. So thank you very much for offering that. And yeah, I probably need to get out there and look myself. So, okay,
Yeah.
Again, any other questions, comments, or concerns? Going once, going twice. All right, folks. Well, listen, be sure to tune in tomorrow. We'll have a great topic then. And with that, I bid you all adieu and have a great evening and a great weekend. Thank you for joining tonight.